Assalamualaikum and welcome back to another lecture 5 teaching video. So today we are going to goes into the 4.2 damper oscillation, which is we want to find the general equation and the solution of the damper oscillation. Now before we go through it here, we have to refer back to our previous lecture, which is about the SHM, the simple harmonic motion. Okay, in simple harmonic motion, I'll give you the example system, which is oscillate in simple harmonic motion. Let's say that we have the here, and then we have the spring, and then we have the lock. Okay, and at the same time we have the ground here, and here the center here is the equilibrium position, which is here, and then right here we have the maximum amplitude, which is x equal to plus a, and here is the opposite, which is x equal to negative a. Okay. Right now, when we pull this object right here at the maximum amplitude and then we release it, what happens here is that the object will start to move to the left and to the right and to the left and to the right, back and forth. Okay, so here in this simple harmonic motion, in this simple harmonic motion, there is the first one, there is no friction. Okay, when there is no friction, that means there is no dissipation, energy dissipation. That means there is no loss of energy, which means that this system will oscillate back and forth non-stop. Okay, it will still move non-stoply under what we call in here in the spring. There is a force in the spring which we call it as the restoring force, which is Fs equal to negative Kf. So this force makes this block to start moving back and forth non-stop, and there is only one force that is exerted on this system, which is the restoring force inside the spring. There is no friction, there is no frictional force. Okay, this because this is like a perfect oscillation. Okay, perfect oscillation, which means that the object oscillates in simple harmonic motion. That's what it means. Okay, so that means when there is no friction, there is no loss of energy. That means that the total energy is conserved. Okay, and here I will show you the force distribution. Okay, so in here there is a force distribution which is Fs. Okay, Fs equal to ma, right? Which is mean there is one force that is balanced by the second Newton's law equation, which is Fs equal to ma, and Fs we know that it is equal to negative Kx, which is equal to mx double dot. Okay, we know that acceleration is equal to x double dot. Okay, and then we want to find the internal energy here. We want to find internal energy. Okay, so what happens here? We will get that negative Kx is equal to m, and then x double dot also equal to negative omega square x, right? So we get that is equal to negative omega square x, and here we can cancel out this one, cancel out, and finally we get that negative k is equal to m negative omega square, and we can cancel out this one more again. Okay, and finally we get that k is equal to m omega square, and here we can derive internal energy of the simple harmonic motion, which is u equal to 1 over 2 k square, and k we can substitute, so u equal to 1 over 2 k times with 1 over 2 times with m omega square, and then times with x square, and finally u is equal to 1 over 2 m omega square x square. So this is the potential energy of simple harmonic motion. And so on, the kinetic energy, we know that K is equal to 1 over 2 ms integral dot square, which is here x dot is equal to v square. Okay, and then finally K is equal to 1 over 2, and then m, and then what is the equation for the velocity of the system? Okay, you know that, right? Okay, or okay, it is equal to 1 over 2 m, and then a square minus x square. If you remember correctly lah, here. Okay, this one, and we have the total energy, which is E total equal to K plus U, and E total is equal to 1 over 2 ms integral dot square plus 1 over 2 m omega square x square. This is the total energy. Right? Alright, now it's good. So far so good. Okay. Now let's go back to here. Okay. From here we have the Fs, right? Fs. This is Fs. And here is Ma, right? Which is Ma. So we know that finally we found that force that is exerted on this spring, okay, it is equal to here, okay, Fs equal to negative omega m omega square x. And notice that this force right here is negative, right? Because this force is directed to the left, right here. The what we call it, the restoring force is directed to the left, so that makes the object to move directed to the left also, which makes the object to move exactly the same as the restoring force. Okay, it's pretty simple, right? Okay, now let's move on to the reality. Now let's look at the reality. So here is the reality. So in reality, okay, let's say that we have a pendulum, okay, in the spring. Okay, and here, let's say that we want to move the pendulum up and down like this, okay, like this. So it means that the pendulum will move to the downward and then upward, back and forth, downward, upward, back and forth. Okay. When there is like here we have the center, which is the equilibrium position, and you know after that down here is the maximum amplitude, and then up here is maximum amplitude. Okay. Now this object, you know that this object, when we do in reality, okay, we move it up and down, and then after that we stop. Suddenly, okay, at the time that this pendulum will stop to move. This is like really reality. It's like how we put this object right here. This object, for example, when we pull this object, when we push this object will move. Will stop at a certain time like this. Right? It stop. Okay, just like this is like this is what we call this the reality. This is what happened in reality exactly. We cannot see this phenomenon, okay, in real life, okay, because this is impossible to do it in real life, almost impossible, because when we start to move this when this system starts to oscillate, okay, it will eventually stop at a certain time. We don't know how long does it oscillate and then to stop. Okay, this is like the reality. This is reality. We're going to see that this is what happened exactly when the system is oscillating. Okay. So in this here, we have two forces exerted on this system. So the first one, let's say that this object is moving upward. Okay, moving upward. Which is velocity down up here. And here we have, like I said, there is a force that is exerted on this spring, which is exactly the same as where the system oscillates. Okay, so here we have the restoring force right here, And at the same time, at the same place, we have the force which is directed upward, which is what we call is the damping force. Okay. So since the object is moving upward, okay, there is like what we call the air that follows the object. Okay, that follows the object, which makes the object going to start to slow. We start to slowly stop. Okay. So I want to show you that the object start to move downward. Okay. Let's say I want to tell you that object is moving downward. Okay. When is this object start to move downward? Okay. There is like a force that start to pull this backward. That makes the object to start to goes back to the equilibrium position, which is this force right here. This ball on the force right here. Okay. So now we're going to force distribution of this the system. Okay. First force is the Fs. Okay, and then we plus it with Fm, which is the damping force, which is equal to Ma. Same, right? The second to one, and equal to also Mx double. Pretty simple. Okay, now let's the relative force is equal to negative gamma x singleton, which represent omega, which is represent as the gamma as the damping constant, and x singleton is the velocity. Notice that then there is like a negative sign right here, which means that this x dot is moving downward. This is x dot. Okay, that's why we want to show that this force is directed upward. So when it is negative, right now velocity is negative, so negative, we'll finally get that this damping force is positive. Same as this one too. Okay, this one is equal to negative kx. Okay, so see that object is directed downward, which is x right here, directed upward, which is negative. Okay, so when it is negative, so this negative and negative here, we'll finally get that this force is directed upward, same as this damping force here. So finally we get that negative kx plus and then minus with gamma x single dot is equal to mx double dot. Okay, and then negative kx again minus gamma x single dot. Okay, is equal to mx single dot double dot. And then we divided each of these equation here with m. We want to remove m, right? So we divided each of them with m. Okay. So finally we get that it is equal to negative kx over m minus gamma x single dot over m equal to x double dot. Okay, and we know that k is equal to here. K equal to m omega square. So we substitute m omega square inside this equation. So negative m omega square x over m minus with gamma x single dot over m equal to x double dot. And we cut off the m here. And finally you get that it is equal to negative omega square x. Okay, and then minus with omega gamma over m x equal dot equal to x double dot. And we transfer all of this to the right side and finally get that x double dot minus omega gamma over m single dot here. This should be single dot. This is single dot. And then minus with omega square x equal to 0. So this is the general equation for the damping oscillation. This is the general equation for damping oscillation. Okay, principle. Okay, notice that in the lecture note, this omega is now becomes what we call that? Omega naught. So omega naught. Omega naught. Okay. So from here we see that S double dot is the acceleration, and gamma is equal to damping constant, and X single dot is the velocity. Omega naught is the natural angular frequency. See? And last but not least, X is displacement. So this means natural. It means that this angular frequency is already existed in the spring. That's where we're going to find another, which is called omega. Don't get confused. There is omega naught and omega. So omega naught is the natural angular frequency in this system, which means it is from the simple harmonic motion, and we're going to find the real omega here, which is what is exactly the angular frequency of the system, the reality. This omega naught is useful in the upcoming topic we're going to go for this. Okay, so please don't get confused. There is omega naught and omega. Omega naught is actually the angular frequency from the simple harmonic motion, but we have the real angular frequency, which is we used to use inside the system. Okay, we'll find out later. Okay, now let's move on. Okay, now we're going to find the real equation of displacement, which is x. So it was found out that the mathematician find out that they found out that xt is equal to e power of alpha t times with the x, my capital X t. Okay, so here is the solution. This is the solution of the displacement for the damped oscillation. Okay, this is solution for displacement of damped oscillation. Okay, and here I'll do some compare. Xt is equal to a sine omega t plus pi naught. Okay, here is the displacement for SHM. Okay, there's difference. Okay, SHM and damped oscillation. And damped oscillation is the reality. Okay, that's good, right? Okay, so far so good. Okay, now let's move on to the derivative. Okay. So we have the at e power of alpha t times x single s capital Xt. Okay. Now here's the toughest part. Okay, we want to find to get this solution. Okay, we have to know that. Okay, we have to know there is velocity and acceleration, right? When we have the displacement, there is velocity and acceleration, both of these components, right? So let's see what is the displacement for this system. Okay, we have the x single dot. We know that velocity, the definition of velocity is rate of change of displacement, right? And it is equal to dx over dt. So that means we have to integrate this equation with the respect of time. Okay, now let's do some integration. Let's do some differentiation. So we have x is equal to e power of alpha t times with the x single dot and x capital X t. Okay, now we want to differentiate it with respect of time. So which is dx over dt is equal to, okay, now we have some multiplication right here. We have a multiplication right here, so we have to use product rule. We have to use product rule. So product rule is dy over dx equal to vu prime plus uv prime. So here we have to do some substitution, which is v is this one. This is v, this is u. Okay, this is u, this is v. So v is equal to x capital X e. Okay, and then we have u, which is e power of alpha t. Okay, now to differentiate this, we found that v prime is equal to dv over dt. It's like we differentiate this equation with the respect of time. So since that this is the capital X, which is the real displacement, okay, the real displacement. So we found that when it is equal to rate of change of the real displacement, which is the velocity. So which is x capital X single dot. Okay, so far so good. Now let's move on to here. Now we have to find the u prime, which is the differentiation of this equation with the respect of time. So here we have to use what is called as the chain rule. This is we have to use the chain rule. Okay, chain rule. So since we have we want to find du over dt, right? So du over dt is equal to du times dt. And here what you want to find, let's say that we want to say dz. Okay, dz. So we know that u is equal to alpha t. Okay, alpha t. Okay, let's not look here. Look here first. Okay, u is equal to alpha t, and we want to find du over dt, which is the rate of change of, how do I say this? No. Sorry. How do I say this? I think I made a mistake here. Sorry. I forgot. How do I say this? Okay. How do I say this? Okay, you know what? Let's just skip here. Okay, forget about this. Okay. U is equal to e power of alpha t, right? So let's just keep that u prime is equal to alpha multiplied with e power of alpha t. Okay, we just differentiate up here, and then we differentiate and we multiply here. Okay, we drop down here, and then we multiply, and then we copy back. Okay, and then finally we get that u prime is equal to alpha e power of alpha t. Okay, now let's do some substitution here. So dx over dt, okay, dx over dt is equal to u v prime, vu prime plus uv prime, right? So what is v? V is x. V is equal to xt, right? X capital Xt. Okay. You know what? I'll just remove t here. So that's easy. Okay. This is x. Okay. And then multiply with u prime, which is u prime is equal to alpha e power of alpha t. Okay. Alpha e power of alpha t. And then plus with the u, which is exponential power of alpha t, which is exponential power of alpha t, and then v prime is x single dot, okay, and then finally we found that x single dot is equal to, which is the dx over dt, we get that it is equal to alpha e power of alpha t times with the x, okay, and then plus with the e power of alpha t times with the x dot. Okay. So this is the first, this is the displacement, or sorry, this is the velocity for the delta oscillation. Okay, now let's look on the x double dot. Okay, x double dot, which is the acceleration, and it is equal to rate of change of velocity, right? So we have to integrate this equation with the respect of time. Okay, slow down. Okay. So that is dx dot over dt is equal to right now we have the more complicated here. Okay. Right now we have to integrate both of these, but I know both of these have to use product rule. This you have to use product rule, and here you have to use product rule. So I'll do it in the next new page right here. So I'll copy back here. So x single dot is equal to alpha e power of alpha t times with the x, and then plus with the e power of alpha t times with the x single dot. Okay, we have here. So to differentiate this, dx single dot over dt, which is the x double dot. So we have to use the product rule. Okay, the first product rule here. Okay, so here I will use it as the I will represent this as the h, and this is I. Okay, so this is final, this is initial. So remember that product rule. Okay, dy over dx equal to du prime plus uv prime, right? So that means final and initial. So final is I, and then times with the u prime, which is h prime, okay, plus with the u, which is u is equal to h, and then I prime, okay, I prime, and then plus with the, of course, we have to do some substitution too, hi, and then this one is j, and then k. So that means b is equal to k, and then u prime is equal to j prime, and then plus with the u is equal to j, and then v prime is equal to k prime. This is equal to that. Okay, now let's do some let I is equal to x, okay, and then I prime, we have to differentiate x with the respect of time. Okay, so we get that it is equal to dx over dt, right? So dx over dt is equal to rate of change of displacement. So this is the x single dot, which is the velocity. Okay. So now let's look at the h. Okay, h is equal to alpha e power of alpha t. Okay. H prime is like we want to do dh over dt, right? So let's look on the chain rule. The chain rule, which is dy over dx equal to dy over du. This is this is dx du. Okay. Now let dy over dx equal to dh over dt, right? So dh over dt is equal to dh dt. Okay, here is what we call as the new what's that called? Like a new form of differentiation. Okay, so I will present it as the du, okay, just du. Okay. Now I want you to see that here we have h equal to alpha e power of alpha t. I want you to see like the power first. Okay, power. So this power, let it as a u. U is equal to alpha t. Okay, like u of alpha t. Now we want to differentiate u with respect of time, which is du over dt. So we get that it is equal to alpha. Okay, alpha. Okay. The first one here. Now let's look on the h. Okay, so we know that h is equal to alpha e power of alpha t, and we know that alpha t is equal to u. So h equal to alpha e power of u. So we want to differentiate h with respect of u. Okay, so we know that this one here, okay, this one can be ignored. Let's look on here. Okay, we know that this is resemble as the e power x. Okay, so e power x, let's say that it is equal to y. Okay, when we differentiate exponential with the power of variable, we will still get it as the same, which is equal to e power of x. So same as this one, which is we get that it is equal to alpha e power of q. It is still the same. Okay, now let's do some of the substitution inside here. Okay, so we get that h prime, which is equal to dh over dt. So h prime equal to dh over dt. So dh over dt is equal to dh over du, which is alpha e power of u, alpha t, which is u. Okay, and then times with the du over t, which is alpha. And finally, dh over dt is equal to alpha square e power of alpha t. Okay, now we substitute here inside here. So alpha square exponential power of alpha t. Let's log on those for now. Okay. Now let's look on here. Okay. Okay, this is a long differentiation. So let j is equal to exponential power of alpha t. So we want to differentiate j, which is j prime, which is dj over dt. We want to differentiate this equation. Okay, this equation with the respect of time. So when you see exponential power of alpha t, of course we have to use chain rule. Chain rule again. Once again, we have to use chain rule. Okay, so this chain rule, okay, the formula is dy over dx equal to dy over du times with the du over dx. Okay, now let's look at here. Okay, we want to find dj over dt. So dj over dt is equal to, okay, is equal to dy over dx, right? We want to resemble this as this. Okay, so find that j over dt, okay, dj over dt is equal to dj over du times with the du over dt. Once again, change let u as a alpha t. Let u as a alpha t. So we want to differentiate u with respect of time, which is du over dt is equal to alpha. Okay. Now let's look on the j. So we know that j is equal to exponential power of alpha t, and at the same time we know that alpha t is equal to u. So j is equal to exponential power of u, and we want to differentiate this. Differentiate the what do you call that? Dj with the respect of u. So finally we get that it is the same like this one. Okay, like this one. So we change it. We just apply the concept. So it is the same. We finally get the same form. Okay. Why? I don't know. That is the rule. Okay, that is the original rule. So we have to apply it no matter what it is. Okay. Finally get the j. Okay, now so dj over dt is equal to dj over du times du over dt. So dj over du is equal to e power of u, which is exponential power of alpha t, and then times with the du over t, which is alpha. So alpha here, and finally we get that it is equal to alpha e of alpha t. Okay, pretty simple. Okay, now we have here. So just do some substitution here. So alpha e of alpha t. Okay. Now let's look on another one, which is k. So k is equal to x single dot. So k prime, it is dx single dot over dt. So this is actually an acceleration, rate of change of velocity. So this x double dot t. Sorry. Okay. Now this is where we do some substitution inside this equation. So we have the x double dot is equal to I h prime plus h I prime plus k j prime plus j k prime. Now do some substitution. So x double dot is equal to I, which is x here, x capital X, okay, and then times with the h prime, which is alpha square, exponential power of alpha t. Okay, very simple, right? And then plus with the h, which is alpha e exponent power of alpha t. So alpha e power of alpha t, and then times with the I prime, which is x single dot. So this is the first row. Now let's look on the second row. Second form. I open another bracket. So k is equal to x double dot, x single dot, capital X double single dot. So x single dot here, and then times with the j prime, which is exponential power of alpha t. So exponential power of alpha t, and then plus with the j, which is j is equal to exponential power of alpha t, and then times with the k prime, which is this one. This one, x capital X double dot. So x double dot. Then close the bracket. Now let's do multiplication. So x double dot here is equal to alpha square e power of alpha t times with the x. Okay, and then plus with the alpha e power of alpha t with the x single dot. Okay, and then plus with the alpha square power of alpha square exponential power of alpha t, and then multiply with x, and then times with the alpha e power of alpha t times with the x single dot. And we have here, we can add up here, and finally we can find that x double dot is equal to alpha square e power of alpha t times plus with the 2 alpha e power of alpha t times with the x single dot here. Here is x, and then plus with the alpha e power of alpha t times x. Okay, very simple. Okay, let me write it properly. Okay, so finally x double dot is equal to alpha square as power of alpha square e power of alpha t, and then times with the x here, and then plus with the 2 alpha e power of alpha t times with the x single dot, and then plus with the finally, which is what is this though? Hold on, did I get it wrong here? Okay, so this doesn't happen. Okay, so power plus exponential power of alpha t times with the x single dot. So this is the acceleration for the acceleration of damped oscillation. Now I will just stop here. I will do some other part, maybe part 3, part 2, I don't know. See you guys in the next one.